Hello, today we'll be introducing you to our Design Day project known as Solstice, or the Space-Operated Lunar Surface Total Internal Contamination Elimination System. We are Team 21074. I am Jody Kreiner, the team lead.
I'm Colin Kelly, the lead research analyst.
I'm Krista Kramer, the safety and quality assurance lead. And I'm Cameron Bradley, the financial manager.
Our project is supported by Paragon Space Development Corporation, with Jordan Holquist acting as our team advisor.
I'm going to start us off by giving a brief overview and background of our project. We participated in NASA's 2021 Big Idea Challenge, which challenges participants to develop solutions to dust mitigation techniques for lunar applications. The presence of airborne dust particles in the cabin may damage equipment, as well as posing a threat to astronaut health, making lunar dust one of the principal limiting factors in missions of extended stay. The development of an effective filtration system such as Solstice is vital to limiting the amount of lunar regolith that enters the cabin after extravehicular activities. Our project objective is to design, build, and test a novel, sustainable, cutting-edge, and cost-effective lunar dust mitigation technique for cabin dust filtration. Solstice is designed to effectively mitigate lunar dust accumulation in the habitat airlock by using a permanent magnet filtration system. The permanent magnet system is incredibly beneficial. Not only is the system highly effective, but it also meets the criteria of weight, cost, and longevity, which are integral factors to consider in space travel.
Now that you have an idea for the basis of our project, we will move on to the actual design of our system. After several weeks of alternatives analysis, we were able to propose the following system, which will reliably, efficiently, and effectively filter out lunar dust from the habitat airlock. After an extravehicular activity, or EVA, on the moon's surface, astronauts will enter the airlock pictured here before entering the habitat. Since this will be the only available avenue of dust contamination into the lunar base, we have decided to focus our filtration efforts in this area. During repressurization of the airlock, directed airflow will be used in conjunction with a vacuum pump to force any lunar dust to the bottom of the airlock. There, the dusty air will be pulled into our filtration system. Multiple passes of the air across the magnets will allow for maximum dust collection. Once the air has been sufficiently rid of dust particles, it can then be recycled back into the main habitat's air supply. A liquid shower system coupled with demagnetization via an iron rod will allow for the magnets to be cleaned of all the collected dust. That dust will then be returned to the lunar surface, and the system is essentially good as new. Because our fully automated filtration unit relies on magnets alone, there is very minimal power requirements and hardly any maintenance required. Here you can see the more technical process flow diagram for our system, breaking down each component. To start, a gas flow rate gauge will be used to ensure proper amount of air is being fed into the airlock at an appropriate speed. Once 1.5 airlock volumes of air have entered our system, a valve will be turned to allow for final repressurization of the airlock. The stream will pass a large particle filter and then move through a three-way valve, which will subsequently close, isolating the magnetic filtration loop. Immediately following that valve is the intricate permanent magnet system, designated in our diagram by F102. Once passing through the magnets, the airstream will encounter another three-way valve, which is initially set to keep the air flowing through the filtration loop. A diaphragm inline air compressor is the driving force of each pass and feeds the stream through an air particle counter before it is collected in the storage tank. This process will be repeated multiple times until the desired air purity is reached. On the last pass, the vacuum pump will activate, evacuating the clean air into an additional holding tank where it can then be recycled into the air of the main cabin. The lower three-way valve will then be switched, opening a line from the magnetic filter to the dust collection container. Another valve will release the cleaning water, while the iron rods are inserted between the magnet pairs, allowing for thorough cleaning of the system. Once the dust has been cleared off the magnets, the water in the tank in T103 will be evaporated, and the collected dust will be returned to the lunar surface.
Our group had the opportunity to test the viability and potential efficiency of the magnetic filter portion of the filtration system. Through an experiment, we were able to determine if the basis of our design was worthwhile to use to achieve the goal NASA had set for us. To test the viability of our design, we performed a series of rudimentary tests. Here you can see a diagram of our initial test setup. An aluminum tube was used as a dust chute and is designated by T101. The magnet pair indicated by M101 is adhered to a mounting plate and spaced with a paramagnetic rod to keep the polarity of the magnets. C101 is the container where the unfiltered dust was collected to determine the efficiency of the system. Here are two pictures displaying the setup of the experiment. The picture on the left is the magnets, as they are positioned on the plate to test for the efficiency of multiple magnets within the filtration system. Here they are positioned at the side of the filter unit. The sifter, located at the top, helps to disperse the dust into the tubing to simulate dispersion of dust as it would enter in the actual filter system. The dust then flows through the tube and collects at the bottom if it is not captured by the magnetic field. The testing procedure was composed of the following steps. To start, the dust is weighed and the initial mass was recorded to determine the amount of dust that is entering into the filter system. That dust is then sifted into the filter system to be captured by the magnetic field. The dust which was not captured by the magnets and fell through the tube is weighed again to determine the unfiltered mass. The captured dust is then collected by moving the filter tube away from the magnets and allowing the dust to drop. This dust is subsequently weighed. Finally, the efficiency can be calculated based on the different weight measurements. This procedure is repeated with more magnets or with more passes until all parameters and iterations are tested. It was found that the single magnet set was able to achieve an average filtration rate of 11% using our testing design. The low efficiency is due to the unoptimized nature of the design, which is related to the dimensions of the tubing and the strength and size of the magnetic field. It was found that the more magnets and more passes resulted in a greater overall efficiency. This image was captured after dust was passed through the filter tubing with a single pair of magnets and a single pass. As you can see, halfway down the tube is the collection point of the dust. This image shows a separation between the filtered dust located above and the unfiltered dust located below. This was a single pass with an efficiency of around 11%. Finally, this is an image of when multiple magnets are placed on the outside of the filter housing and how the dust is collected within the housing when multiple magnets are present.
In conclusion, we can state that our main objective was met. We successfully designed and built a filtration system that we then used to test our hypothesis. Overall, our testing results proved that it is possible to capture dust simulant using a magnet filter. This then led to some calculations to determine the optimum number of passes as well as the total magnetic surface area in order to achieve the desired filtration efficiency. More advanced testing is necessary in order to determine further details about the rest of the system. One of the biggest challenges we faced as a team was that we were not selected by NASA to receive funding as part of the Big Idea Challenge. Therefore, we had to modify and simplify our design in order to be able to finish the project with significantly less resources. Also, our project is quite different than most of the projects that our classmates were assigned, and therefore it often did not fit the class assignment rubrics for our design class. Finally, since this project is based on a novel technology system, we did not have access to data from previous research to base our design on. In order to continue to develop this technology, it is vital to produce a full-scale model of the prototype and test the materials in a thermal vacuum environment to ensure proper operation in the lunar setting.
As we wrap up a year of work developing this novel solution to a unique problem, we would like to thank our team sponsor, Paragon, and specifically our mentor, Jordan Holquist, for helping us produce the best project we could. Although there were many challenges along the way, the support offered to us by our industry partners and the U of A engineering faculty went a long way in ensuring our success throughout this process. We thank you all for your time and support.